We are moving today into the last part of databases, which is the physical design of the database. And I have up here a kind of high-level diagram. The book had it, I think, in chapter 2, that gives you an idea of where we've been and where we're going. So we have that a database has different levels. And we started with the conceptual view, which is the one provided to users. And when we were doing the conceptual view, that was chapter 6. And it was chapter 6 where we were talking about SQL and how you could select information from a database, how you could insert new rows, how you could delete rows, and how you could update rows. Then we moved into chapter 7 and talked about the internal view, which is the DDL, how you set up the database using the data definition language, and you establish the relations. And as part of that, you can also create views with the data definition language. The other thing that we have to worry about is how we physically implement the database, how we map relations to physical files and secondary storage. And that's what we're going to be talking about for the next week. Now, one thing you don't see in here is the design step, but the design step was also kind of in here because the ER design or ER diagrams and normalization are both things that you do, design techniques you use in order to decide what your relations are, and only once you've decided what your relations are you able to then use the DDL to create them. So that was what we were seeking to do with the ER design. So we're down now to the lowest level, which is the physical implementation, and that's what we'll be talking about today and on next Tuesday. Thursday is fall break, so we won't be meeting on Thursday. Now, just to also give you an idea of things. So where we are is that we are, this was wrong because today is the, whoops, it's the wrong semester. Okay, so where we are is right here with physical database design. You can see that in 2 weeks we'll have a midterm exam. And you'll see that after next Tuesday, we have this catch-up day. Okay, well, we really don't have anything to catch up on. So actually what I plan to do is use that as an exam review day. So on 10/12, we will be reviewing the material and getting ready for the exam. And I've actually did this last semester in 365. I felt like the exam scores improved because I did it, but it only works if you show up. So I actually think that that's a pretty important day. So that's what's happening. I know it's early. I'm not going to talk about the midterm exam today. I'll do that next week. But if you go to the sample exams, someone asked about it. There is a sample midterm from last fall, and its solutions that are up. So you can take a look at that for the general format of the exam. Let's see. Also, whoops, you will note that the homework assignment is kind of a dual one. It's actually covering both normalization and it's covering physical design. So it's covering two different things, and therefore it's actually due in 2 weeks, not in 1 week. Fall break is also intervening, so there's nothing due this Friday. But also note that there's no late acceptance on that one, and the reason is because of the exam. I need to be able to make the solutions to homework 5 available immediately so that people have an opportunity to study over the weekend. Normally I don't release the homework answers until 3 days later because that's when the last of the late assignments can come in. But homework 5 and the last homework this semester is like that too. I don't take any late acceptance on them, so I can immediately release the homework solutions. And quite frankly, with 2 weeks, you should have plenty of time to finish. Okay, so moving into today's discussion. Need to make sure I'm in the right year. There we go. So the goals of physical design are twofold. We want to map our relations into files on the file system, and there are different ways to organize files. There's an unordered, well, just quickly going ahead, there's 3 ways we can do that. We can use an unordered file, which is called a heap, and that is something that most of you are familiar with text files. We can use something that is an adaptation of a binary search tree called a B+ tree. And we can use something that is an adaptation of a hash table called an extendable hash table. So we will probably get a little bit to B+ trees today. We'll finish them on Tuesday, and we'll also start and finish extendable hashing on Tuesday. So that's one thing we have to do, is map relations generally into one of those 3 types of files. Generally, your database management system will give you a choice of file type, and based on the characteristics of the relations, which we'll talk about, you'll choose one of those particular file organizations. Then the second big thing for physical design is selecting indices to aid the query processor. So how we organize our relations on a file matters, but also we can provide additional indexes on different attributes that will aid the query processor, and we'll talk about that as well. An index is a lot like the card catalog at the library, helping you to find things quickly. So before we do that, we have to talk a little bit about file organization on a disk. And how much do you cover in 130 disk organization? Yes? No? Always seems like the answer is not really. So I tend to go over it because it seems like some of you know it, some of you don't. So we kind of have to talk about what is secondary storage. Secondary storage is where we store long-lived information, as opposed to short-term memory, which we refer to as RAM, and which disappears when you turn off your computer. And secondary storage traditionally has been stored on disks. However, there's now a competing technology called solid-state memory, which is faster but also more expensive than disks. My computer uses solid-state memory to store things. So we're going to talk about both disk and not so much about solid-state memory, even though things are moving to solid-state memory. A lot of, I would say that still most databases are primarily stored still on disks. So the big thing about disks is that they are slow. It is much more time-consuming to access something on a disk than it is in main memory. And the reason for that, well, first of all, a disk is kind of what you might expect. Looks like a platter. and you have then a collection of platters sitting on top of each other, kind of like a bunch of dishes. And these dishes are spinning around at a high rate of speed, okay, up to 15,000 revolutions per minute. Probably some that are even higher at this point. And you have a read-write arm that is going in between these disks. So here's our disk, here's the read-write arm, and it's coming in and it's settling at some part of the disk. And the disks are organized into what are called tracks. So the read-write arms are coming to rest at a certain track. And as the track spins under the read-write arm, it's able to read data off the disk or off that track. And it could read off of any of the platters that it's at that point. But all the read-write sensors are fixed. So at any one time, they're all over the same track number, just on different disk platters. And there's hence two things that are going to slow us down. First of all, if we know that, let's say we know that the information is somewhere on this track right there. So in order to get to that track, we first have to move the read-write arms to that track. That's called seek time. Okay, it's the time to move the mechanical read-write arm to the appropriate track. But even when it's gotten to the appropriate track, it's still not necessarily yet able to read the information. Why not? Maybe at the wrong place in the rotational cycle. So the track may have to rotate under, so when we get there, maybe when the read-write arm arrives, this is where the track, this is where the track currently is. It has to come around and under the read-write arm, because the read-write arm doesn't rotate, it's the platters that are rotating. So that's called rotational latency. It's the time for an appropriate sector of track to rotate under the read-write arm. Well, both of these are slow operations. In RAM, the access is via electrons, essentially, so it's at the speed at which electrons travel. But that's not true for seek time or rotational latency. That's mechanical. Both of them are mechanical, and that's much slower than moving electrons. Hey, if you look at Wikipedia, its numbers actually are a little old, but I had trouble finding anything more recent. Seek times, they're quoting texts from anywhere from 2010 to 2012, but when I was looking for more up-to-date information today, everyone was either quoting Wikipedia or saying that seek times really aren't improving. So it seems that that data or those statistics at Wikipedia are pretty up to date. So for high-end enterprise grade disks, it's 3 to 4 milliseconds seek time to get your read-write arms to the correct track. For your average desktop device, it's 9 milliseconds, so laptop. For your average mobile device, it's 12 to 15 milliseconds. Sorry, I said laptop. That's a mobile device. That's 12 to 15 milliseconds. For a desktop computer, it's 9 milliseconds. So when you get untethered, it's even slower. And actually, for CDs and DVDs, it's even slower. It's around 65 milliseconds. Really slow. But that's not a big deal because on CDs and DVDs, you tend to get there and then you stop and you're just sequentially reading, so they don't have to be fast. Okay, and then rotational latency times depend on how fast the disk is spinning. So at 15,000 rotations per second, it works out on average to about 2 milliseconds. Partly that's because when you go there, you only expect on average to wait how long? If the full rotation is 4 milliseconds, you would expect to wait on average 2, because on average it's halfway away. So that's part. So at any rate, they go from about 2 to about 7.15 milliseconds. So that's pretty slow. Okay, so just to get to a piece of data on a, say you're probably using a high-end enterprise grade disk for a database, but you're still probably looking at 3 milliseconds for the seek and 2 milliseconds for the rotational latency. That's 5 milliseconds. And that's only 200 disk accesses at most per second if you have to keep moving it. Plus, you're not the only one who gets to use it. Other people also will be sharing it. So you may not even get 200 reads per second. Plus, you have to transfer the information. And there, it's actually not much difference between consumer grade and enterprise grade. So the most consumer grade hard drives will transfer data at about 200 megabytes per second. So once you're there and reading, the transfer rates are about 200 megabytes per second. And for enterprise grade, it's only at most about 50% better. It's from 200 to 300 megabytes per second. And there's one thing I need to just go back. I kind of hinted at it when I was drawing it. The tracks themselves are divided into what are called blocks. So on each track, you have a track. The tracks are divided into blocks. And the operating system will determine what the block size is. On Unix, it was traditionally 4,096 bytes. Not sure if that's gone up or not. I've heard sometimes 8K rather than 4K. At any rate, the operating system determines the size of the block. And that's the unit you read. You use a block. You read a block. So even if you only want 100 bytes, you end up reading the entire block. For this course, we'll assume that they're 4,096 bytes. So you read 4,096 bytes, even if you only want 100 bytes from the block. And what happens is that comes in over a bus into some buffer, and then the bytes you want is served into your program. Okay? But the key is if you're searching different parts of your database, so you're moving the read-write arms, you're only getting at most 200 reads per second. That's pretty slow because today's computers are typically capable of executing on the order of hundreds of millions of instructions per second, and yet you only get 200 reads. So you might only get 200 records or 200 rows per second. So the CPU is going to be really bogged down. It's called I/O bound. If you probably at least in 130 heard the word CPU bound and I/O bound. Yes? No? No? No. Okay. Well, CPU bound means when the CPU is the thing that's working all the time and the disk is pretty much idle. And I/O bound means that it's dependent on the disk. You're waiting for the disk to bring information into memory, and the CPU is waiting. Now, because CPUs are time-shared, typically they can be working on other tasks at that moment. However, if you're on your laptop, you may not be performing another task. All you're doing is waiting for the operations to finish, and then I/O bound can be an issue. Seriously, how many of you have had 361? You must have discussed this in 361. Okay. Not in 130, though. I just realized as I was talking, 361 would cover it. Okay. So, reading blocks into memory, and the goal is to try to read as few blocks as possible, but also to get to them as quickly as possible. So in your courses thus far, when you read a file, you typically start from the beginning and read sequentially all the way through it. Okay? But as you might imagine, if you're doing a select operation on staff at the University of Tennessee and you want to select the employee record for Brad Vanderzanden, you're not likely to find me at the beginning of the file. You're more likely to find me where? At the end, after you've done a lot of useless reads. So you would like to be able to maybe have an index that would allow you to go to the index, just like a card catalog, and quickly identify which platter, which track, and which block my tuple is contained on. So typically that information would be a disk number, a platter number, a track number, and a block number. So those would be the elements of a disk address. So you might have a pointer in memory, short-term memory, but on secondary storage you typically have a disk address that shows where something is located. Okay, so we're going to have a goal of intelligently choosing indices on different attributes like last name so that we can efficiently look up information. Now before we do that, we should also talk about, very quickly, solid-state devices because they are rapidly supplanting hard disk drives. In fact, how many of you have solid-state drives on your computers? Okay, so about half of you. For the half that don't, I highly recommend it. Okay, things open up much more quickly. For example, here's Word. Double click. Does it open up that fast for you on your hard drive? I doubt it. Okay, things just open up much faster when you have solid-state memory. Okay, and the reason is it's not using moving parts. It's using persistent solid-state memory. I'm not a hardware guy, so I can't tell you exactly what type of memory it's using. It's not as fast as random access memory, but it's still pretty fast. So, for example, the transfer times on your cheapies are actually as good as the transfer rates on your enterprise grade hard drives. And on the top end, they are literally 10 times faster than your enterprise hard drives at transfer rates. Plus, no moving parts. The seek times are typically less than 0.1 milliseconds. So that's the time to locate where an item is to get to, in effect, the read, whatever read mechanism to that part of the solid-state memory is less than 0.1 millisecond. Okay, that's a lot better than 3 to 4 milliseconds, plus whatever your latency. There's no latency here because there's no rotation. So you get to where you want to be much faster. I think it's 0.08 to 0.16 is actually the typical seek times for solid-state memory. At any rate, it is much faster to read from solid-state memory than it is to read from a disk. And that's true for both finding the piece of information, getting the sensor to the proper location, and then the transfer rates are much higher. Now, write times are a little different. Write times for less expensive SSDs, like the ones in your laptops, can be actually significantly slower than the read rates, up to 10 times slower. I don't know exactly what it is in mine. For higher end SSDs, such as the ones you would find in a database, the write times will be comparable to the read times, but you'll pay for that. So for consumer grade SSDs, currently you can expect to pay about 24 cents per gigabyte, which is about 4 times more expensive than what you would pay for a hard disk drive. So you'd pay about 6 cents per gigabyte for a consumer grade hard disk drive per gigabyte. So you pay about 4 times more, but the performance, believe me, is worth it. Okay, so no matter whether we read, however, from a solid state device or a hard disk drive, it is slower than from RAM. So we definitely want to allow us to get rapidly to the right information using what is called random access. So what you've typically done with your files up to now is what's called sequential access. You start at the beginning and you read all the way through. That's sequential. And what we want is something called random access, where we can access any element, so directly access any record in a file. Now you're going to see me dropping down into the terminology of file systems. So remember that when we're talking about physical memory, that a relation becomes a what? What do we call a relation when we're talking about physical storage? No, actually, good guess. The guess was table, but that's actually the user view. File. So you'll often hear me use the word file. For tuple, it becomes record. And for attribute, you're often going to hear me use the word field. I'll be using them interchangeably, but if you hear me use file, record, or field, those are the corresponding terms for the relational model. Hey, it's just different jargon when you get to the physical layer. Okay, so as I said, you have these basic organizations. It could be unordered. That's actually pretty rare to have unordered. You're normally going to store it either as a B+ tree or an extendable hash. And does anyone remember from either 140 or 302 why you would ever use a B tree over a binary tree over hash tables? Because hash tables are faster for inserting, deleting, updating. Range queries, very good. So the reason you use binary search trees when you are in data structures class is because you may want to access a range of data. Like you may, for a race database where I'm a runner, so I care about running times, you might want to know all runners who finished between 15 and 16 minutes in a 5K. So that's a range query. It's asking for all records in a certain range. Or you might want everyone whose salary is between 30,000 and 40,000. That's a range query. Or the bookings. You want it all bookings between February 1st and February 10th. That's a range query. Okay, you want everything in a range. So there's two types of queries that we care about. They are range queries and what I call point queries. So a range query asks for a set of tuples where an attribute value falls in a range. Whereas a point query, you're typically looking for a single record, or so ask for a tuple where an attribute equals a discrete value. And it could be, you might say, like where X in London or Glasgow or Knoxville. That's still a point query. A range query is what uses the less than or less than equal. That's a range query. If you just say where X in A, B, C, that's a point query. That's a point query. That's asking for discrete values. A range query involves inequalities. So it's typically on numbers or on names or on dates, which are numbers in some sense. Okay, so we have basically two types of file organizations. If we expect something to be frequently used in a range query, we would typically want to represent it as a B+ tree because that's derived from a binary search tree. And if it's a point query, tends to be involved in point queries, then we're probably going to use an extendable hash table because it's based on a hash table, which is typically faster than a binary search tree. Okay, so when we are organizing our file or determining how to arrange the tuples in a file, you'll often hear something called a cluster key. And it is basically the attribute or set of attributes that are used to physically sort the file. And they improve the performance of range queries. So typically, the way the records are arranged is in a B+ tree. So typically, tuples are stored as a B+ tree. The reason is because typically we want to have them ordered in some way. So we call the way in which they are physically clustered either the primary index or the cluster index. And the distinction is only whether we cluster on the primary key or whether we cluster on a non-primary key. Okay. It turns out it's pretty rare to cluster on the primary key. Okay? Because the primary key is an artificial key. How often are we going to be asking for a range of artificial keys? Almost never. Okay? So paradoxically, most files are not actually ordered on their primary key. Most files are ordered on a non-primary key, like last name, or race time, or date. Probably the booking relation would probably be by date or by guest name, would not be by guest number or booking number. So in fact, most files have what is called a cluster index rather than a primary index. Okay? So that's what the physical organization is. And then the remaining indices are called secondary indices because the file is not physically organized on those attributes. Instead, it's a subsidiary index that helps us gain access to the records. So the idea with a cluster index is that the things are all next to each other. If this is A and B and C and D logically in the tuple, then logically on the file, A, B, C, and D are together. And E, F, let's say G and H are on a separate track, then logically on the disk, E, F, G, and H are together. So cluster means that if they're logically next to each other in the attribute domain, they're also next to each other physically. But a secondary index says no. Even if they're logically next to each other in the attribute domain, they are not physically co-located. So in that case, if this is our file, we might have actually H here and A here and B here, and so they're all over the place. They're not physically co-located. Okay, because it's a secondary index. So a secondary index, because it's not using a range, is typically going to be a extendable hash table. So typically these are going to be a B plus tree, and this secondary index is typically going to be an extendable hash table. Because secondary indices are not physically organizing the file. So we need to choose the indices which attributes to index so that we can help the query optimizer find records efficiently. So first of all, we're clear on what indexing does. It's kind of like a card catalog. It points us directly to where we want to go. Okay. So one option would be, well, why don't we index everything? Sounds good. Why don't we just put an index on every single attribute in every relation? Okay. Well, there are some issues with that. If we are inserting or deleting a lot, what are we going to be doing with all of our indices? Updating them. And those indices, for the most part, exist where? In main memory? I think not. They exist primarily in secondary storage as well. So if we have a whole slew of indices, then every time we insert a tuple into a relation, we're going to have to update all the indices that depend on the attributes in that relation. So in fact, it's not necessarily a good idea to put an index on every attribute in your relation. Okay, so there are some rules of thumb about what can be done. Okay, so these are the rules of thumb, and that's what they are. They're not thou shalts or thou shalt nots. They're just general rules of thumb. So generally, we put an index on the primary key of a relation if it is not the cluster key. Okay, and the reason, why do you think we would typically index the primary key? There's an operation that's involved in a boatload of times, even if it's an artificial key. Join. So it's going to be involved in a lot of joins. We probably don't want to be doing a sequential search through our file looking for the primary key. So we probably want to put an index on the primary key of a relation. And for the same reason, we're typically going to put a secondary index on all of our foreign keys because they are also frequently involved in joins. So 1 and 2 tend to be no-brainers. It's very rare that you wouldn't choose to index your primary and foreign keys. After that, it becomes more of a rule of thumb. So you tend to add secondary indices to any attribute heavily used in selection queries. Well, that can be relative, but you probably would look over time at your logs to figure out what, initially you take a guess. Okay, initially you don't have any transaction logs to look at, but over time you'll get logs and you can look at what is frequently being queried, and based on that you might choose to add some attributes that are being heavily accessed. On the other hand, if you misguessed initially and you chose to index some attributes that aren't being heavily hit, you might choose to remove those indices. So you don't just choose them at the outset, at the inauguration of the database, and then ignore it. You periodically will fine-tune the performance by looking at your logs, because you typically log activity, and try to improve it. Okay, it's also common to add secondary indices on attributes that are involved in order by clauses, group by clauses, and other operations that involve sorting, such as union or distinct. Okay, and the reason is, if we are commonly saying group by, then it would be nice if the attribute can be accessed in its alphabetical or numeric order. If I'm often saying group by branch number, then, group by branch number, it'd be nice if they were in some index so that we can easily get to them. So anything involved in sorting tends to get a secondary index on it. Another one that frequently gets them is attributes involved in aggregate functions for a very interesting reason. Okay, it's actually 5 and 6 is kind of combined. There's something called an index-only plan. So some queries can be solved or satisfied. Some queries can be satisfied by looking only at the indices. Okay, so for example, let's say I asked for the minimum and maximum salaries in our company. Well, if we happen to have a secondary index on salary that is, it actually doesn't matter whether it is a B+ tree or an extendable hash table. It's going to be far faster to just look at the index rather than at the tuples. Can someone tell me why? Okay, let's pretend it's ordered first. That should be simpler. Let's say I want to know the minimum and maximum salary because I just look at the first and last entry in the index. That's a lot faster than having to look through the entire file. If we haven't clustered the file on salary, which is unlikely, then the only way we can find the minimum and maximum value is a sequential search. That's pretty awful. Okay, so if we have an index and it's sorted, then it's very quick. We just go to the first or last entry in the index. But now I'm making another claim, which is, let's say that the index is an extendable hash table, and we all know hash tables aren't sorted. My claim is that if I'm trying to find the smallest or the largest salary, it's still faster to go into the index rather than to go through the table sequentially. I say my claim now is it's faster to sequentially go through the index. Yes.
Is it because you don't have duplicate salaries in there, like they're all in one spot?
See, that's a good one. I hadn't thought of that. So partial is that you won't have duplicate salaries necessarily in the index. You'll have the salary and then multiple pointers. So there'll be fewer salaries in the index, but that's not the primary reason.
Less discretes?
Pardon?
Less discretes?
Less discretes. Why?
Because you're only looking at the index file instead of the full.
That's right. Because basically you can cram, so basically the size of the salary field, size of salary, is probably much less than the size of the tuple, which means far more, many more salary per block than tuples per block. Which implies far fewer reads on salaries. So the index takes up much less storage, so reading it sequentially is going to be faster than reading the file sequentially. So even if the index isn't sorted, it's actually still faster to find the minimum or maximum salary by simply looking at the index. So that's called an index-only plan. You look only at the index to solve the query. If you're doing count, that's good to look at the index. If you're doing total, that's good to look at the index. If you're doing average, all of those aggregate operations can be solved by looking only at the index. It's far faster to look at the index. So generally, we add a secondary index on attributes that are frequently involved in aggregate operations because those operations can be solved only by looking at the index. Okay? A cute query optimizer might, no, let's see, is that true? No. That generally index-only plans are pretty restricted to aggregate functions. Okay, so those are good attributes to put indices on. So what are things not good to index? Small relations. So the branch relation in pretty much any branch, unless you're an enormous company, is not going to be worth indexing. If we have 50 branches, how many blocks do you think 50 branches are going to fit into in a database? If you have 4,096 bytes, that's about 80, you could get 80 bytes per branch. How many blocks for 50? How many, and let's say that each branch takes up 60 bytes. How many blocks will we need for the branch relation? 1. Why index it if, remember, you have to read a block no matter what. You can't avoid reading the entire block. So why index something if it's going to occupy less than 1 block of memory? Okay, because you're going to have to read it anyhow. So any index you use will simply increase the number of block accesses, because indices are also kept on secondary storage. So not only will you have to read the block associated with the index, you also have to read the block. And all entries in the index will point to that one block. So we don't tend to index small relations. For the same reason, probably even if we needed 2, we needed to go big and go with 2 blocks rather than 1 block for the branch relation, there's still a good chance we're not doing any indexing. Why? Well, let's see, the index costs us a block access, and then we have to read a block. That's 2 block accesses. Oh, well, if we just read the file, that would also be 2 block accesses. No win there. So generally with small relations that only occupy 2 or 3 blocks, we're not going to index them. By the way, we can probably hold them in memory anyhow. Okay, we'll just cache them. So for that reason also, there are caching strategies. We probably just hold those files in memory. Okay, here's the killer though. An attribute or relation that is frequently updated. Well, what does that mean? That's completely subjective. That's where it gets down to the art of fine-tuning. Okay, because an attribute might be heavily used in selection queries, but it also might be frequently updated. So, should you index or not? Often the only answer is to try it both ways. There's a lot to be said for empirical experiments. You index it for a week and you see how fast the queries are. Then you take it off and you do it for a week and you see how fast. And whichever is faster is what you choose. So there's often, it's hard to a priori know. This is very, very subjective, an attribute or relation that is frequently updated. Okay, the branch relation probably isn't frequently updated, but hey, it's small. Okay, actually the staff relation probably is not frequently updated. Okay, but in the hotel one, what is frequently updated? Booking. Okay, hotel, room, and guests probably aren't updated that much. Even guests probably is not updated a lot in the context of things. But booking, unless we're going bankrupt, hopefully gets updated a lot. Okay, so we're going to have to think long and hard about whether we're going to index things in the booking relation. Well, guess what? Probably you do need to still index the guest number in the booking relation, and you probably still need to index the room number and the hotel number because they're going to be accessed a ton. And probably date from and date to too. Actually, not date to. You very rarely need to know date to in a query. Date from is what you need to use, right? When you pick up the phone and you call, no one ever says, the operator never says, oh, what day are you checking out, sir? Or, what day are you checking out, ma'am? There's always, when are you checking in? So don't get suckered into just thinking, oh, if I do date from, I also should index date to. No, actually you shouldn't. You should index date from, but not index date to. Date from is the one that's going to be showing up all the time in your queries. Okay? And here's something that always gets people, which is if an attribute will retrieve a significant proportion of the relation, you shouldn't index. And it might look like, you might say, okay, the expected number of records per block is roughly 1. So maybe blocks store 100 records. And on average, the query is only going to return 1 record per block. And you think, wow, that's only 1% of the database. That's not that much. How about wrongamundo? Okay, because if it on average returns 1 record per block, well, on average, we're going to look at every block. So what was the point of the index? Because we're reading every block anyhow. Unless those records were physically clustered, in which case they're all going to be together. But if they're randomly scattered throughout the relation, then an expected number of 1 record per block means we expect to pretty much access every block in our file. So in fact, we shouldn't be indexing unless the number of records per block that we expect the query to return is considerably less than 1. Okay, we only expect it to get at a few blocks. And then here's one that also is a bit of a killer. We don't like to avoid indexing attributes that consist of long character strings. What typically is a long character string that we might probably look up a lot? Address is one. Name. Okay, both of these aren't very good. So why are long character strings bad? So let's think about a typical tuple. Might have 50 bytes. Let's think about the address of the branch. Roughly what percentage of the branch tuple is probably occupied by the branch attribute? 50 bytes in the branch. If I just tell you it's 50 bytes and I say what percentage of the branch, you can take a back of the envelope guess. 30%, 40%, 50%, big number. It's not 4 bytes, it's not 8 bytes. Probably a minimum of 20 or 25, right? So we're looking at 40 to 50% of the file. So what that means is that when we index a long character string, we're actually, in effect, creating a second file of almost the same size. If we choose to put an attribute or an index on the branch address, that index is going to be at least within a constant factor, pretty small constant factor of the original file size. That's not too good. So we really hate indexing long character strings. That said, last name is looked up a lot. So how do you think that gets reconciled? There is a way to reconcile it. Yes, Dustin.
Put a limit on the data type on how long the character string can be.
You could put a limit on the character string, and actually that does bite me occasionally when my name shows up as Vander Zandy, and that happens. So yes, sometimes they put a limit on the size of the field. Sometimes they actually shorten my name in another interesting way, which is they think that I'm egotistical and I write out my middle name. So it comes out as Brad V. Zandon. That's a good way also of shortening my name and also making it hard to find when I call up on the telephone. But there's actually another way of doing this, which is we often make the cluster index be the last name. So in the staff directory, the last name is often the cluster index. So not always, because you don't often do range queries on last names, but last names we would like to index. They sometimes end up as cluster indexes. So they're basically used to physically organize the file. So now we kill 2 birds with 1 stone. The problem is we don't normally do range queries on last names. So that's a trade-off. But if you're in the staff directory, really, do you really do a range query on salary a lot? Probably not. Now, if it was the race database, I would make a strong argument for you might do range queries on times. I certainly used to do it because I used to like to know who my competitors were. So there you might be more likely to put the cluster index on time rather than last name. But I guess what I'm trying to make the point here is generally we avoid indexing long character strings, but last names are the one exception. We normally end up indexing them somehow because we do so many queries involving last names. Okay, same thing, we would probably index the hotel name because quite frankly, even though many of you were hard coding the hotel number, which I told you not to do, but most people don't know what the primary key is for hotel number. They don't know it. The operator, when you call up and say, hey, I want the Marriott Inn in Knoxville, they don't immediately say, oh, the hotel number for that one is 038121. So you typically have to index hotel name or you index last name. So I guess what I'm saying is proper names often get indexed. Okay, but again, this is highly subjective. These are just rules of thumb, and you have to take a guess, an educated guess, and then you fine-tune it. The book spent a lot of time talking about, oh, why don't you analyze the transactions? Well, in reality, it's pretty hard to analyze transactions in advance. You probably are going to more look at your logs from beta testing and start doing it from that rather than doing, I mean, you're going to take a guess. You'll index your foreign keys. You'll index your primary keys. You'll probably index your proper names. You'll index a few other attributes, and then you'll take it for a spin and kick the tires. So don't get wound up in chapter 18 with their long, convoluted discussion of transactions to analyze. In fact, just ignore it, because I won't be testing you over it. Okay, I will be testing you over this stuff. I expect you to know, in general, I may give you an attribute on an exam and say, are you likely to index it, yes or no? And you tell me why. If I say hotel number, you say, primary key, probably going to be a secondary index because it's artificial and it's involved in a join. I give you the date to attribute for the booking relation, and the answer should be no. We're probably not going to index it because generally a query isn't for date to. Most queries are for date from. Now I know that some are for date to, but they don't come up nearly as often. Remember, you can't index every attribute. So it's a relative thing. And relatively speaking, date to is simply not accessed nearly as frequently as some of the other attributes in the booking relation. So you'd probably be not indexing date to. But you probably would index date from because that is frequently used in lookups. So questions about this?
So the cluster index was just an index that the storage of the file is then actually changed for?
Yes, the file is physically organized. Records are if two records are logically next to each other because of the attribute value, like last name, they will be physically next to each other. And the difference between a cluster index and a primary index is that the cluster index is on a non-primary key. And the primary index means the file is physically clustered on the primary key. So both a primary index and a cluster index refer to a file that's physically clustered on it. It's just different terminology. Yes?
If you wanted to use more than one cluster index, you need to store the file twice.
Yes. If you want to use more than one cluster index, you would need to store the file twice, and that never happens because then you have a completely redundant files. So you just suck it up and you do it once. Okay, you're right. So if you wanted 2 cluster indexes, you'd have to store the entire file twice. But you wouldn't do that. It's just too many issues. So basically, the answer is you only ever have 1 cluster index. Yep, or primary. It's one or the other. Yeah, one or the other. Either or. Whereas you can have as many secondary indices as you want. You can even put a secondary index on 2 attributes, but that would be kind of uncommon, meaning a pair of attributes. Other questions? Okay. So, I have 5 minutes. I'm just going to quickly motivate why you don't use a hash table or a binary search tree in secondary storage. It might be, why is he going to spend a lecture torturing us with B+ trees and extendable hashing when I could probably just use an AVL tree in secondary storage? I mean, why not? So I'll take an example from the handout that I had, which is up on Canvas. Let's say you have 10 million driver license records for the state of Florida. Probably higher than that now, but let's just say it's 10 million. And let's say that you can store 100 people per block. So there's a million. Actually, that's not it. Actually, the index itself has to store 10 million names. So you have 10 million names in your AVL tree, and log 2 of 10 million is roughly the depth of your tree. And I think that's roughly 24, something like that, 24, 25. You can do the, if I'm wrong, someone can tell me. But I think your tree is roughly 24 or 25 levels deep. Okay, well, if you do this in secondary storage, each node is going to be an access. It's going to be a block access. So if you're going down like this, each node is a block access. Well, remember what we said, that you get only about 200 block accesses per second. And I can pretty much guarantee you that a lot of queries are done on the Florida license plate by the DMV around the state. So there's contention for it. So you're not getting exclusive access to that file. There's a lot of other people around the state also getting access to it at the same time. So you're not getting your 200 accesses. Let's say that you're sharing the database with 10 other people at that time, so you're only getting 20. So now we're taking over 1 second just to do one query. That's not very good. Okay, so the problem is our branching factor stinks. And on any kind of large database with a large number of records, a binary search tree is just going to require way too many disk accesses. Okay, and it turns out that hashing isn't any better. Hashing, well, when we get to extendable hashing, I'll make the same point and show you. But hashing has a similar issue, which is that you end up with too many block accesses if you're doing hashing. So basically, researchers were like, but binary search trees and hash tables are good. They're the best data structures we have for in-memory searching. Can't we somehow modify them so that they would work well on secondary storage? And the answer was much easier for search trees than it was for hashing. It took until, I think, the early 1980s or even early 1990s before they figured it out for hashing. But for binary search trees, it was pretty easy. What do you think the answer was for binary search trees? More branches. So they just are going to cram a lot more keys into each node and have a lot more branches. And if you have a lot more branches out of each node, it means you'll have far fewer levels in your tree, and you only have one read per level, so you will get to your leaf far faster with a bushier tree. So that's what a B plus tree is the idea is we just have far more records in each node, or keys actually, not records, far more keys in each node, and we have a far bigger branching factor. So we will get to that on Tuesday. We will also get to extendable hashing on Tuesday. In the meantime, have a good fall break. My homework assignment is such that you do not have to work on it over fall break. So enjoy.